We have heard him already today, but some of you joined us later, so I'll introduce Professor C.S. Rajan again. Professor C.S. Rajan did his MSc in Mathematics from IIT Kanpur. He obtained his PhD from Tata Institute of Fundamental Research, Mumbai, and postdoctoral research at McGill University, Montreal, Canada. He is currently a professor at TIFR, and professors' main interests are in arithmetic geometry, automorphic forms, and representation theory. From now, Professor.
Okay. Thanks. Yeah. Thanks, organizers again. As I said, it's really a great pleasure to be here and interact with all of you. So at the outset, it's been, I should say that I know I've had some interactions with all these three, Akshay Venkatesh, Scholze, and Kosha Birka. In fact, even had some nice dinners and beers with Scholze and Kosha Birka. And I should say they're all very great people, very easy to interact with them, totally unassuming given the kind of levels of mathematical accomplishments they've had. So it's quite very easy to get along, very nice. And I remember Akshay Venkatesh I asked him about entropy at Kumbakonam. He's getting the Shastra Prize, and and very beautiful explanation. And it is true that that is one of the attributes which is said of Akshay Venkatesh and Scholze and all. You talk to them, they will explain to you things in a far more clearer manner, what you are thinking about, or even whatever concepts they are thinking about, which you don't see it so easily in books or other material. It's a really amazing talent Akshay and Scholze have. It's very risky. Okay, so what's happening? There are both Akshay and Scholze are in some sense they are all number theoretical. This thing work is on number theory, and what in the morning we saw was we are looking at quadratic forms, say ax squared plus bxy plus cy squared. So for instance, so these are what I would say a is greater than 0, b is greater than 0. These are positive definite. So in the sense these are a, b, c are integers. C are integers. Positive definite in the sense they on z2, z cross z minus 0. It maps to this quadratic form maps to positive reals, positive rationals. Okay, cube, positive integers, natural numbers. Okay, and that's one. And what happens is we also fix the discriminant. B squared minus 4ac, which is equal to delta. In this case, I'm going to be delta is less than 0. Let's work with that. So the example which you are looking at in the morning, for instance, x squared plus 5y squared, the discriminant delta is minus 20. And there is another discriminant form, say 2x squared plus 2xy plus 3y squared. Again, this discriminant delta is also minus 20. So I've written only these two forms. The reason being that what happens is, if I have a form, I can send x equal to some, say x dash equal to ax plus by, and y dash equal to cx plus dy, and where abcd is what is called in SL2Z. That means determinant 1 and integral entries. Okay, so these are invertible transformations. Of course, I could take determinant equal to 1. Okay, and integral entries. Determinant could have been taken minus 1 also, but let me just take determinant 1 and integral entries. So when I do this, the quadratic form Q, if I take, so I should have said, if I take a quadratic form qx dash y dash, then it gets mapped to some, say q dash, then it gets mapped to some qxy. Right? I substitute for the variables x dash and y dash, this thing. And what one can check is that the discriminant of q equal to discriminant of q dash. Okay, so the discriminant is preserved. Okay. So then I said what you can, so you have this discriminants are preserved. So what happens is you can make a transformation. Suppose for instance I take this ax squared plus bxy plus cy squared, and I make a transformation which is x goes to say x plus k for some integer, and I fix y to y. Okay. So let's see what happens to this. So then this becomes a into x plus k whole squared plus b into x plus k y plus c into y squared. Okay, so I can write it ax squared plus wait, sorry, x plus ky. Right. So then I get ax squared plus and the mixed term will be 2ak plus bxy, and plus the other term which is ak squared plus bk plus c into y squared. Okay. So now what the reason I want to do is this, if I take this is what is called a shift operator, it's a shifting along one this thing. So then I want to say 2ak, wait, let me go back. So the quotient, the middle quotient is 2ak plus b, and I want to make, suppose if b is greater than a, right? So let me prove it here. If b is greater than a, mod b is greater than a, okay. So then what happens is, by looking at the remainder mod 2a, I can assume that 2ak plus b, 2ak plus b, this is by taking the remainder mod 2a, I can make 2ak plus b less than or equal to a. A is positive, so it's a. So what I can do is I can make this coefficient less than. See, and the discriminant, okay, I should also say the discriminant b squared minus 4ac is bounded. So let me say this other thing. So okay, now the other thing is b squared minus 4ac is fixed. Okay. Okay, so anyway, so what I can do is, in this way I can get mod b less than or equal to a, and by flipping I can also ensure it is not easy, by either changing x or y I can make a less than or equal to c. Okay. So this such a form is called a reduced form. Okay, the examples for discriminant, so discriminant minus 4, the only reduced form of discriminant minus 4 is x squared plus y squared, and discriminant minus 20, the only reduced forms are those two, x squared plus 5y squared and 2x squared plus 2xy plus 3y squared. These are the same. As I said, the other form, this is also the same discriminant, but they are equivalent under the SL to Z transformation. Okay, so this is, I am not stating the proof, but it's fairly easy given the various constraints. I have said that the discriminant is equal, that there are only finitely. So basically the moral is there are only finitely many reduced forms. Okay. And the point is that as far as representation of integers by quadratic forms are concerned, these reduced forms are enough. You don't have to work with it because they are equivalent. All other forms are equivalent by an SL to Z transformation, and you can read off the integer values by knowing for one of the reduced forms. Okay, so that is only finitely made. But the interesting point is all the conjectures of Fermat, Euler, and many others, and which goes back in some sense to the Diophantus and Brahmagupta, is this idea which I said that if P and Q are congruent to say 3, 7 mod 20, that implies PQ can be expressed of the form x squared plus 5y squared. So what this means in this language is that I can write P is 2x squared, because it's not of the form x squared plus 5y squared, I said it, 2x squared plus 2xy plus 3y squared. For some x and y, this is P, and Q is 2u squared plus 2uv plus 3v squared. And this I can write it as some capital X squared plus 5y squared, where x will be a function of some function of x, y, u, v, which will be kind of linear in each variable, but bilinear. You will have x, so it will be xu, yv, xv, yu, all those 4 variables, and similarly y also has this. Okay, so this kind of structure is guaranteed to us, and in some sense this the quadratic form x squared plus 5y squared by the Brahmagupta identity is the identity element. So this, so what happens? So x squared plus 5y squared into u squared plus 5v squared is again of the same type, the w squared plus 5z squared. Okay, so it is like the identity element which is there. Okay, so what Gauss did is that Gauss said that these equivalence classes, this reduced forms, equivalence classes, or what you call reduced forms. This is just an abstract set, but it is imposed by the various numerical relations one can see by whatever we saw in the morning, that as a structure of an abelian group, as a structure of a group. Okay, and what one says is that this group is called the class group. It's called the class group of what is called. So you can attach a quadratic field of the field of quadratic rationals. So here, what in this case x squared plus 5y squared is in this case it will be z root minus 5. Okay, because you are taking so this is z root minus 5, but so this, in this case, this group is just consists of 2 elements. It is z mod 2z. It has an abelian group. Okay, so in general you are going to get a finite abelian group. Okay, now the question is, what can you say about the structure of this group? What is the structure of the class group? Of the class group. Right? So this is what one is interested in, and the class group saying in this manner is a very complicated thing in terms of binary quadratic forms, but luckily thanks to maybe, I don't know who it is, either Dirichlet or Kumar, there is a beautiful, or Dedekind, there is an interpretation of the class group in terms of the ideal class group of number fields, and that makes it easier to work with. But this is anyway one of the this thing, right? Okay, so so there was a heuristics, Cohen and Lenstra. I don't know, the understanding is, suppose I want to know in this class group how often there is an element of order 3. Say for instance, they looked at many questions. For instance, how often there is an element of order 3. Okay. Now, if you know some things about abelian groups, finite abelian groups, if 3 divides the order of a group, finite abelian group, so or any group, then there is an element, there exists an element of order 3. Okay, so what you can ask for, so how often does 3 divide some number, integer is 1/3. So 3 divides a number n, so or n is divisible by 3, so the chance probability is 33%. Right? But of course you are counting finite abelian groups up to some isomorphisms, so there might be some different structure and such things. So essentially they say that you will but these class groups are a special class of finite abelian groups, but they say it almost occurs with the same probability that you would expect that 3 divides an element of order 3 appears in an abstract abelian group. Almost. There is some heuristics as to when, because there are some natural small conditions. So apparently the Cohen-Lenstra heuristics predicts that for 3 divides is 43% is what the Cohen-Lenstra heuristics predicts. So for instance, how often does 2 divide? The class group was solved by Gauss himself. That's called the genus problem or whatever it is, and it was solved by Gauss. Okay, but for 3 or many other factors, there is this heuristics which are not really understood, and I should say that again, since it's a more informal gathering, I should. I was at the institute, and Langlands after lunch, I was just gossiping with a colleague of mine as usual, and from India, no, Deependra, and Langlands comes and says, he wanted to know about class groups and various things, how often something, and then suddenly it just occurred to me, and I said maybe you should look at Cohen-Lenstra heuristics, and and then Langlands left, and then we continued with our chit chat, and after half an hour or 1 hour, then Langlands comes down and says that was exactly what I wanted to know. I went to the library and checked it, and so this was in 2006 or 7. And Langlands had a lot of conjectures and other things on trying to understand this Cohen-Lenstra heuristics. And so Akshay Venkatesh was looking at this kind of aspects, and so what I got thanked by Langlands also, so I should be very happy. Okay. Anyway, so what Akshay Venkatesh, together with I think Ellenberg and one more person, Westerland or whatever. So what they do is to prove these heuristics. But I should say the class group and the behavior is extremely mysterious. For instance, let me say there is a whole conjecture of Gauss. There are only finitely many. The largest discriminant is 169 or 168. There are only finitely many imaginary discriminants, as I said, negative discriminants, positive definite, which has class number 1. Okay, that was called Gauss's class number 1 problem, and that had a very beautiful solution. Of course, it was solved around 60s by Heegner and essentially by Heegner. There was a beautiful solution by Goldfeld using elliptic curves like what Vijay Patankar was talking about, and the reciprocity law. Okay, so Akshay Venkatesh with his collaborator Ellenberg and they proved this, but conjecture, but not over number fields, but over what is called over function fields. So let me say what are these function fields. Function fields over finite fields. Okay, so so this is, so just say that this is an amazing proof, because what they bring in is some amount of topology which is not clear that this topology is a correct one, and some very recent topological things which is called homological stability and things like that to prove this conjecture. So it seems really a fantastic technical and an idea tour de force. Okay, so just keep that aside. Let me say about some other problem, which is an analogy. So this is both for Akshay Venkatesh, Scholze, and Kosher, Birkar. So let me say a bit of what is analogy, which is standard and which goes into a lot of reasoning behind mathematics. So what we know is, we know the ring integers Z, and you can take, for instance, complex numbers, the polynomial ring in one variable. This is everybody understands this notation. This is the ring of polynomials in one variable over Cx, and or in fact you can work over any field Kx. For instance, I will be working with the other thing is the finite field Fpx. Okay. So here what happens is this Z is a unique factorization domain. So in all these things, the Euclid algorithm is valid. division algorithm is valid. Holds. So in particular, this is a unique factorization domain. So every number up to a unit can be written uniquely in terms of some irreducible prime elements. Okay, so for instance, Z has a unique factorization. So what is Euclid algorithm? In the case of polynomials, if I have any polynomial, and you can write any polynomial and Q times suppose let's take, if I take two polynomials A and B, A equal to BQ quotient plus remainder R, and where either R equal to 0 or degree of Q is less than degree of B. A and B are given one, and degree of R. Degree of R is less than degree of B. Right? In the usual integers, one knows the thing. So this is the Euclid's algorithm. So this these are unique factorization domains, and okay. So what one does is that you are looking. These rings are in some sense analogous. They satisfy various properties which are very similar. They are what are principal ideal domains. So unique factorization, not more than these are what are called principal ideal domains. Every ideal is generated by a single element. Okay. So yeah, but there is a difference between Z, Px, and the general ones. The point with Z and Px is if I look at Z mod prime ideal Z mod Pz, so this has finite cardinality. As cardinality, finite cardinality. And similarly, because it's Fpx, when you are looking at Fpx modulo any irreducible polynomial, suppose if I take some P, so what you'll be left with is counting polynomials. So by the remainder theorem, you'll be left with counting polynomials of degree less than degree of P, but the coefficients are constrained to lie in Fp, so this will also be finite. This cardinality is also finite. Okay. Okay, so there is roughly an analogy between number fields and function fields. These are called number fields. These are called function fields because they are polynomials. They can be thought of as functions on some spaces. This thing, but Fpx is, for instance, one of the polynomial. This thing. These are function fields or finite field. Okay, right. So then the analogy is one of yeah. Right. So what Akshay Venkatesh and Ellenberg prove is that you can talk about the class number or the equivalence class of binary quadratic forms or in terms of ideal class groups, and they showed that the finiteness, the Cohen-Lenstra heuristics hold. Cohen-Lenstra heuristics hold for what are called for Fp, not only for Fpx is not really the correct this thing, but for such rings. So these are for rings similar to this, for what are called function fields or finite fields. Function field of course or finite fields. So another example will be, you can take Fphi, you can take x comma y, and then go modulo something like y squared minus x cubed minus x. This is the thing y squared equal to x cubed minus x, which was discussed in Vijay Patankar's talk in the morning, and think of elliptic curve. So you are taking two variables, but you are having one equation, so it basically becomes a one variable function field, and you can work with this. So for such types of fields, the theorem of Akshay Venkatesh and Ellenberg and I think Westerland or Vigilant holds. So that is one analog of the one theorem which Akshay Venkatesh proved. There is that the Cohen-Lenstra heuristics hold. Okay, so this is one aspect. So now let me go on to another aspect of the theorem of whatever Akshay Venkatesh's work. So what happens is when you look at quadratic forms of x squared equal to y squared equal to p, and similarly other thing. So more generally, this is a very specific quadratic form, or I could form x squared plus 5y squared is what are the numbers, like n is of the form pq, what are the values it takes and things like that. So what this led is to look at the values taken by quadratic forms. Right? So you are looking at a quadratic form, and or generally by, you can look at, say, yeah. So then so this has again a rich history. You can generalize a number of variables. You can look at, for instance, x1 squared plus x2 squared plus x3 squared. So when is a number can be written, when is a prime can be written as a sum of 3 squares. So that as we can check, the only counter examples are when p is congruent to 7 mod 8. So it's equal to p if and only if p is not congruent to 7 mod 8. Right? I suppose this is true. So so this was done by Gauss, and there are other things about triangular numbers and things like that which you can get. For instance, so there is the theorem of Lagrange, which is that if I take a quadratic form in 4 variables, x1 squared plus x2 squared plus, every number can be written as a sum of 4 squares. Every number, every positive number, every natural number can be written as a sum of 4 squares. Okay. So now what there is a very important starting point of what is called Legendre, which is called a local global principle. So what the name is this thing. So what Legendre or other says, suppose if I take an equation which we did with this, suppose x squared plus y squared equal to p, and we ruled out primes p congruent to 3 mod 4 by simple congruence computation mod 4. That if you take a square, the square mod 4 as only 0 or 1, and so if I take the sum of 2 squares, it will only leave the remainder 0, 1 or 2. So which we did that, right? So you can of course, this can be converted into not immediately, but x squared plus y squared equal to pz squared. So I have added an extra variable. It just lends some homogeneity to the problem, and you can look for when x squared plus y squared minus pz squared equal to 0, for instance. Because you are looking at rational numbers, but you can this thing. So there is a bit of this thing, but you can ask for some such similar questions, right? So what? So for instance, what Legendre was looking at. Suppose if I want to look at things like x squared plus y squared equal to 3, the same condition. Okay. So this 3z square, this does not have solutions. This does not have integral solutions. See, there we looked at 4. Here the natural thing is to look at 3. So what happens is we can always assume that we can clear out, if suppose if a prime p divides x and y, then p squared divides x squared, p squared divides y squared, and then 3 is a prime, so p at least will divide z squared. So we can cancel out p. So what you can assume to prove this is you can assume that x and y are relatively prime. Okay. Now I go mod 3. Okay. So what happens is if I go mod 3, so then I will have that x squared plus y squared is congruent to 0 mod 3. Yeah. 0 mod 3, right? But so the only way this can happen, the squares have residue 0 and 1 mod 3. So the only way this can happen is both x and y are divisible by 3. Because if even one of them is not divisible by 3, then that square will have residue 1. And then if it has both of them are not divisible by 3, the square will have residue, the sum of the squares will have residue 2. So the only way this will happen is that this thing. So this is not possible. Okay, so a simple congruence works, leaves out such thing. So what Legendre said is that suppose such simple counter examples are not there, then this is Legendre's theorem. Then there is this equation, say ax squared plus by squared plus cz squared equal to 0 always has a solution. So of course I will have to assume that a, b, c do not all have the same sign. If a equal to b equal to c equal to 1, then the equation will be x squared plus y squared plus z squared, and that is always positive, and it is 0 only when x, y, z equal to 0. The trivial solution is always there, so we are counting only non-trivial solution in this homogeneous case. Right? So what does it mean to say what is this simple counter examples? The point is we are looking at solutions in integers, and essentially there is a ring homomorphism to any z mod nz. This is the aspect of taking, suppose if I say n equal to 10, I am looking at the residue, the remainder mod 10, right? And this, as I said, preserves addition and multiplication, taking remainders. So that is what it means to say it's a ring homomorphism. So if there is a solution in integers, so the local global principle is this thing: a solution in integers, solution in Z implies solutions in Z mod nz for all n. Okay? So for everyone, z mod 2z, z mod 3z, z mod 5z, z mod 10z, z mod 100z, whatever, all the things, there is a solution. So the question is whether the converse holds. So local global principle, LG principle, is does the converse hold? Okay, so that was proved by Legendre. So for the form, as I said, ax squared plus by squared plus cz squared, not all ABC of the same sign, and provided locally at every, if it has a solution in z mod nz for all n, has a solution for all n, and they have at least one of them has different sign, otherwise just by so then this quadratic form equal to 0 has a solution in integers. Right? Okay, so that's a thing which is there. And of course, mathematicians, we are jobless people, so we want to generalize this, and for whatever, for just the sake of doing it or whatever, it's a beautiful theorem. It's a very beautiful proof. Again, it goes back to the same Brahmagupta identity for so the proof, I should say, essentially depends on the Brahmagupta, the Diophantous Brahmagupta identity which we talked about. That is what is called that the norm map is multiplicative. Norm map is multiplicative. So what I would say is the norm of suppose a plus 5 root b minus b square root minus 5 is a plus b square root minus 5 into a minus b square root minus 5, which is equal to a square plus 5b square. Okay, so this norm map is multiplicative in the sense if I take norm of two such elements xy is equal to norm x times norm y, where x and y are of the form a plus this. Okay, so that's what the Brahmagupta identity, and it depends on that. Okay, so now one of the generalizations is I can take a quadratic form in some number of variables x1, x2 to x100. I can substitute for xi some linear combination, say a11 ai1 plus whatever plus ai50 y50 and so on, right, x1 to. So I can substitute in this thing, so I'll get a new quadratic form. But in 50 variables. See, I'm given one quadratic form, fix a quadratic form, say in 100 variables, and I get a new quadratic form in 50 variables by substituting various matrices, 100 cross 50 matrices. Okay? In this way, what are the quadratic forms we get? What are the quadratic forms in 50 variables we get? See, when I ask for, right? So if I'm asking for x squared, yeah. So the point is, of course, what one would like to say is that you have to ensure that the local obstructions, which is essentially, as I said, Z mod NZ and things like that, should not be present. So that's a standing thing. So the question, so then the current state of art, which was in 1978 or whatever, is that if the local obstructions are not present, and if the number of variables, suppose I substitute, so if n is greater than or equal to 2m plus 4 or whatever it is, so this n is the larger set, and you are substituting, so n is the number of variables in x1, x2 to xn, so this is the number of xi variables, x1, x2 to xn, and then I am substituting each xi in y1, y2 to ym, so I get this thing. So it should be less than half the number of variables in xi, then you get all quadratic forms. So this is somewhat like theorems of Lagrange, that if I take x1 squared plus x2 squared plus x4 squared, that represents all integers. Okay, so you get this thing. So this was the state, and people thought that at the maximum you might get 2m plus 3. But this was difficult to get. So what Akshay Venkatesh Ellenberg did, is to say that it's enough to say n greater than or equal to, I think, m plus 5. Right? n plus 5. So they cut down this 2 to 1. Okay? So this was a result of Akshay Venkatesh and this thing. This was considered, almost nobody even expected this, and they proved this. But it was not only the result, but also the method of proof was interesting. So the method of proof was also interesting. So the point I should, if you read some of the things about Akshay Venkatesh or whatever, it is not only that the theorems are not expected, in the sense they were either expected to be very difficult or not expected, but the method of proof also used very beautiful novel techniques, recent techniques or recent high-powered results from different areas to bring to force on this, which are not expected to immediately give such results. For instance, in the Cohen-Lenstra heuristics, he used methods from what is called topology of this Hurwitz moduli spaces and some homological stability, which looks quite different in order to control the properties of the class groups of this function fields. Here what he did is he used ergodic theory, and here there is a very strong Indian component also to it. So what happens is there is a conjecture which is due to Dani and Raghunathan. Again, they were which was proved by Marina Ratner, one of the most significant works in ergodic theory, which has found a huge number of applications in number theory. And what Venkatesh and Ellenberg do is to do this, use Ratner's theorem to prove this theorem. So let me say that why it is surprising. See, ergodic theory is something which talks about chaos or things. You know, when is a flow chaotic, right? That is what is basically means ergodic, that it kind of flows all over the place with, except for leaving measure 0 or some such thing. So ergodic theory, you know, basically they are ready to throw out measure 0 sets, which means it can be anything. But for number theory, you are counting, you know, numbers are measure 0. But what they, as Akshay Venkatesh says, is that using ergodic theory, we prove the existence of a rational point in one of these spaces. So you are trying to say, you know, ergodic theory doesn't bother about measure 0, but you are saying there is a specific one point which you want, a rational solution. So that is quite amazing, the way they have done it. Of course, I should say that I have no idea of what the proofs are or the methods are. So just, this is all dream work. Okay, so please excuse me, but anyway, okay. But I'm happy Dani and Raghunathan was my advisor, and of course Dani was a senior colleague. These are one of the best results to have come out of the conjectures from the Tata Institute and from the Indian mathematics. So it's really a beautiful piece of mathematics which has been used by Venkatesh and Ellenberg. Okay, so I've said things, and okay, so let me. So there's one more. Again, I've introduced the actors in the thing. So a third piece, which I'm just going to say what is happening, but let me say the thing. I don't know the conjectures, but it's supposed to be a very exciting piece, and many of my colleagues are excited by this work of Venkatesh. Which is, what is happening is, we looked at the group SL to Z. So this is one of the most important groups, in the sense of, as we saw, it kind of governs symmetries of spaces. So this is what is called an arithmetic group, or, you know, the entries are all integers, and it's one of the most interesting groups. And you can generalize it. You can look at SL and Z and so on. The various n cross n matrices with determinant 1 and integral entries. Okay, and what we also looked at was, we can look at the space ax squared plus bxy, cy squared, the space of quadratic forms xy, right? And here, so far I had assumed AB are in integers, right? ABC are in integers. But take ABC in reals and look at the quadratic form only up to scaling. Only up to scaling. Okay, so this is an example of what is called a symmetric space. So this is what is, if you want, is isomorphic to the upper half plane. No, I remove this. The real n is not included. This is isomorphic to the upper half. Maybe both upper and lower half plane, but I don't know. But yeah, but essentially it is this. Okay, and what you are looking at equivalence classes of quadratic forms under SL to Z. So you want to look at the symmetric space S, modulo the quotient, the equivalence classes by SL to Z. Okay, so this is, in some sense, one of the principal objects of interest. These are the objects of interest. Okay, and so what the conjectures of Akshay Venkatesh is to say, in some sense, that the topology of these spaces has some very interesting parts dominated by symmetry. So the topology has some interesting components. Okay, so that's a part which I should say that my thesis was on one of these topics, and it almost broke me. So I just couldn't do anything for 8-9 years, or rather 5-6 years, and so the first thing I did after finish, I will not come back to this. I'll do something. So okay, no, but these are topics which are very interesting. It's a very beautiful set of things. So this gets tied up with another famous thing, which is, so let me say, these conjectures of Venkatesh. The reason they are interested is they get tied up with the reciprocity laws. So this is another thing which I only briefly touched. I didn't say that. So the reciprocity law in the morning I said is that suppose -5 is a square mod P, right? That's what happens with if and only if P falls into some congruence classes. P is congruent to 1, 3, 7, 9 mod 20. So these are what are examples. So what it says is to know whether some number is a square, when is it a square mod P for which primes, that's a complicated problem, but the solution is very simple. It falls into some finitely many congruence classes mod sum 4 times 5, the discriminant 20 or whatever it is. So that is the nature of reciprocity law, that the problem seems to be non-linear, but the solution is an absolutely simple linear recipe. Okay, so there is a long story from there, but when you want to prove the other Fermat theorem, that there are the only solutions of x power n plus y power n equal to z power n, or the trivial solutions for n greater than or equal to 3, what Wiles and Taylor-Wiles did is to show that reciprocity, generalized reciprocity between elliptic curves, which are equations of the form y squared equal to x cubed plus ax plus b, cubic curves in 2 variables, sufficiently nice, and something modular forms of the type Ramanujan talked about. Okay, again, this is a, if you really want to, for some time, this is the most amazing piece of work by Ramanujan, the conjectures of Ramanujan. So let me just say what that. So what Ramanujan, I don't know whether you know this function called the tau function of Ramanujan, tau n. So I will not get into the definition, but the point is that if I take this y squared equal to x cubed plus ax plus b, right, and so this gives you, so you look at the discriminant of this cubic form, the discriminant of this cubic thing, discriminant, and so this discriminant function you can write down. There is some uniformization going on, and so the discriminant function lives on this upper half plane, which I talked about, this quadratic forms, and mod SL to Z, which I talked about. It's not really a function on SL to Z, mod that it has some behavior with respect to SL to Z. It has some very nice homogeneous behavior, scaling behavior with respect to SL to Z. Or let me say that in terms of quadratic forms, this discriminant function, this thing, delta of lambda q is lambda to the power minus 12 times delta of q. Maybe, yeah, I suppose this is correct. Okay, So this is what it behaves. It doesn't really quotient out a function on SL2Z, but it behaves like this. Okay. So the discriminant function, I'm thinking of it as a function on the quadratic forms. Don't ask me how, but anyway, this. So then Ramanujan made the following famous conjectures. Tau of PQ is multiplicative, tau of P times tau of Q. And then there is a recursion relation for tau of P power n. Let us not bother with that. And the last thing is that tau P mod of tau P is less than or equal to 2 to the power P 11 or 2. Okay, so see, of course, modular forms were looked at before by Jacobi and many others, but what they were looking at was the theta functions and other things. But these are the eigenforms. The later theory was developed by Hecke. This what is called these are eigenforms for Hecke operators. So there is a lot of hidden symmetries which are manifesting for every prime P and whatnot, which gives you this hidden symmetries, and what happens is this discriminant function is an eigenfunction for those hidden symmetries. So they are kind of preserved by those hidden symmetries. They are called the Hecke eigen operators, right? And so these are the conjectures that Ramanujan led to this theory of Hecke eigenforms, and then in general to the Langlands theory and other things. So what the Wiles reciprocity law is to tie up elliptic curves over Q to this eigenforms of weight 2. This is a super generalization of class field theory of quadratic reciprocity, and really maybe one of the most fundamental breakthroughs in the last 150 years. At some point of time, I don't think anybody even thought that this kind of theorem could be proved in the coming 100 years. At least I remember sitting in a colloquium. Sayre was talking about the conjectures and in Bombay, and it said, so what? No, everybody has gone over time, so I'm allowed. I want to come and say my bit. It's okay. I don't think most of you are interested, but let me just, at least I will have a satisfaction. I haven't come to Scholze's work, so it has. So elliptic curves over Q to eigenforms of weight 2, and yeah, so it was just considered impossible. I think people thought, okay, Sayre said it, but the feeling was, okay, it will take still another 100 years before the Shimura-Taniyama conjecture can be proved, and then within 5-6 years, Wiles had gone ahead and almost proved it, but with a little bit of help from Taylor-Wiles, it had the same. So this conjectures of Akshay Venkatesh is trying to make sense of this Taylor-Wiles method in higher dimensions when you want to generalize it. So that is what made it interesting, because the Taylor-Wiles method is not so easy to understand, but apparently yes. But I'm just quoting, okay? That's it. So now I said let's just a bit. Let me spend some time about. Okay, let me finish off Kosha-Birkar or whatever it is. No, let me get to Scholze. Yeah, so Scholze is in some sense a real phenomenon. There is no doubt. Yes, kind of, everybody now wants to, in arithmetic geometry or whatever it is, wants to learn what Scholze has done. So, for instance, there is Arizona Winter School, where usually I don't know many people go for learning when to understand some of the materials which is presented. But apparently for Scholze's work, there are 450-500 people in the audience, which is a huge thing. You're working in arithmetic geometry, it's a very complicated thing. So many people are trying to understand and use it in their thing. So Scholze is really, is one of the minds which people say comes only once in a while. So it's a very amazing creativity. So he has kind of introduced new ideas and new spaces. So new spaces. Again, it may be very the thing. So when I said, so let me just give me the thing. So when I said this Legendre's local global principle, we have to look at things like Z mod nz. But Z mod 10z, for instance, this what is called the Chinese remainder theorem, breaks up as Z mod 2z cross Z mod 5z. Okay, so essentially what happens is, in order to understand these rings, it's enough to understand Z mod P to the power kz, where P is a prime and P and P k is some power. Okay, so then mathematicians find it's useful to put this all together. So you have what is called what is called periodic numbers, and they are exactly the completions of Q. So if I take rationals and I complete it with respect to the distance x minus y, the distance norm, so then you get what are called real numbers, which we think we understand. And but you can complete it with respect to divisibility. There are norms which are divisibility by, say, 5, 7, 11, 13 and so on. Okay, when you do that, see, you say two numbers are close in the fiadic metric if they are highly divisible by power of 5. Or two numbers are close in the 13adic metric if they are highly divisible by power of 13. Okay, so then you can complete that, and what you get are what are called the periodic integers, periodic numbers, ZP. So Legendre's theorem can be said that a quadratic form has solutions over integers if and only if it has solutions over all the completions of Q. Okay, stated in this form, it's easier to prove Legendre's theorem than in the older form because it has this thing. So the point is that ZP is a ring which Vijay Patankar did say something about what you call characteristic. So this is what is called a characteristic zero ring, whereas the Z mod PZ is a characteristic P ring. So characteristic 0 means n times 1 is not equal to 0 for any n. The characteristic P here, P times 1 equal to 0. So that's why it's characteristic P. Okay, in Z mod PZ. So what one does is that instead of looking at only the Z mod P, Z mod phi Z or Z mod phi squared and so on, somehow what it makes sense, which has been again often the case in mathematics, is that instead of studying an individual object, like you want to know whether a polynomial of the form, whether any cubic polynomial is solvable or any quintic polynomial is solvable, instead of looking at just that polynomial, you look at the set of all such polynomials, or you look at fields associated with that and argue in terms of a bigger structure, and then you can talk about a single thing. So in some sense, going to the limit, it helps by going to the limit that the periodic numbers are easier to study than the individual ones. And then if you want some information about the individual ones, you try to come back by what are called control theorems. Not the control theorems which you heard in the morning, but by some other listen. Okay. So this is what the periodic things are happening. And what Scholze has done is to introduce new geometry in the context of periodic spaces. And which allows him, so this what happens is that allows him and others who knows the subject to go from, so the characteristic 0, which is what is of interest. So these are the rationals, integers and other things. Here is what we are interested in as number theorists. Okay, but then it allows him to derive results out here by going to what is called positive characteristic greater than 0. These are the positive characteristic. And but here the point is, here we are doing arithmetic number theory, which is difficult. The advantage of going to the function fields is you do geometry. So the language of geometry has been greatly enhanced by this person called Grothendieck, who used various methods of topology and other things, which is related to another conjecture. So I should really say that conjecture before this thing. So Grothendieck allowed, so what happens is you use geometry and the Grothendieck machinery and the developments henceforth were kind of, after Grothendieck geometry became easy, any man in the street should be able to do algebraic geometry was a statement made by some people. And so you use geometry to solve problems in number theory. So this was a two-way method, so what is called Scholz's tilting method to go from characteristic 0 to characteristic 0. So just let me say, one of the most exciting developments which in number theory which happened. Okay, so the point is, which tells you what the work of Grothendieck and others, which is this. So you look at, for instance, as you can look at, suppose an equation of the form x squared plus y squared minus 5z squared equal to 0, or you can look at y squared equal to x cubed minus x, right? An elliptic curve or something. You look at various polynomial equations and do that. As I said, part of the local global principle is you look at the solutions in z mod pz, say z mod phi z, z mod sound z, and so on. Okay, so you look at the solutions. The point is these are all finite, so you can count. These are finite. You can count the number of solutions. Count number of solutions. Okay, so I should say that this whole story was started by Emil Artin in an attempt to try to look at Riemann hypothesis, the standard Riemann hypothesis, which I am not going to talk about now. What is called the analog of the Riemann hypothesis, and he started making these things, and Hilbert called him aside. Young man, what are you doing working in the wilderness of mathematics? Work on something more important, central. Of course, this became the most central aspect of mathematics, but Artin could never get back to this. Okay, yeah, Artin started the game and he didn't left it. Yeah, but Hilbert, this thing. So much so for Hilbert's insight into mathematics. Of course, he is great, but I just say even the big people can be wrong. Okay. Their negative opinions should be discarded. Positive opinions can be taken. Okay, but anyway, so the point is that you can count the number of solutions. And so the amazing fact, which was finally this thing by André Wein, he was also a person who loved India and came to India quite often, or rather had a soft corner for India, is that when you look at the number of solutions, as the say p varies, as I should say, let me say p varies. Don't ask me this thing. So you just count, and from here you can read off the topology of the space of the complex space y squared equal to, say for instance, if I am looking at x cubed minus x, that means all solutions in complex numbers, xy in complex numbers, right? As he said, the real topology, the curve looks like this. Okay, so there is the curve looks like this, some cubic equation, which every line meets in 3 points. There is one figure out here and some other holes. So the what are called the genus and various things and whatnot. But you can read it off. This, of course, some part of it goes back to calculations of Gauss, but this is. So what is amazing is that just by looking at the number of solutions, you are able to read off the topology. So what Grothendieck finally did is to define a topology on spaces or finite fields. Notice these are finite fields. If you look at the standard topology, these are all discrete set and whatnot, but Grothendieck was able to define a notion of topology on spaces or finite fields. And so this has proved to be extremely effective or useful in all work which has been done later. And what Scholze has been able to do is that when he's able to define these p-adic spaces and other things, this topology, or what is called the action of the Galois group, is also carried on. This what the Étale topology has an aspect that there is an action of what's called the Galois group or the fundamental group on it, and this also gets carried on, and so that is what Scholze does, which is okay. I think I'll stop here. Maybe I won't get Cauchy-Beaucard basically is, as I said, you look at Z, the analogy between Cx, but Cx can be thought of as, if you want, functions on the sphere Cx. These are rational functions, P upon Q. P and Q are rational polynomials. This can be thought of as holomorphic functions on the Riemann sphere. And similarly, you can look at the quotient field of Cx by, say, y squared minus, say, x cubed minus x, and so on. Right? These are called rational functions on the elliptic curve and things like that. And one of the aspects is how to classify these algebraic varieties or these algebraic spaces. And the point is that the function fields give you or enough to classify these things. And there is, for curves in one dimension, it was understood long back that you get some very nice models which are called in every function field. And what you want to do is to classify such function fields in dimension 2 was done by Italian geometers long back, and classified finally by Codera, Shafarevich and others in the 60s. Okay, but mainly the work of Codera. And the question was, what happens in dimension 3? So this has been an ongoing program, and Cauchy-Beaucard worked at what are called, how do you get good models for varieties of dimension 3. Okay, so that's a kind of thing which Cauchy-Beaucard, again, I can't say anything more. Maybe I can, if you want, I can say something about what's happening in the dimension 2 story, but not in the dimension 3. Okay, so that's work. So most of, let me just stop here. Yeah, okay.
So we are at the end of the conference now. So I will like to give vote of thanks. So first of all, thanks to NBHM for giving me funds or giving us funds. This is 9th edition, and you won't believe last 8 editions have been supported by NBHM. So without their support, we just cannot really have this conference. So thanks to Professor Balsubramaniam, especially to, and Dipendra Prasad and others for helping me, and from application form to everything, they made sure we get enough money. Secondly, I would like to thank, of course, director who is extremely enthusiastic about RMIT. In fact, from month of April or May, he starts calling me, saying what is progress in RMIT, have you started calling, have you decided whom to call and on. And that is the push, that then we get feeling, oh my God, it's already May, I have to start working on it. So thanks to director. Then after that, obviously, RC and Dean Academic, he helps me in everything. And this time Murli also helped to get this room. So my special thanks to Murli for giving me R103. Yeah. So this is me means organizing committee, okay? It's not Manisha Kulkarni. So myself, Srinivas, Vivek and Raghavan and Prasanna. So it's not me equal to Manisha Kulkarni, me equal to organizing committee. So after that comes to all this office staff, like in Padma, Nirmala, Cynthia, Pushpa, financial department, and all of them managed. They just told me that don't worry about money, we will just handle it, you concentrate on academic part. And registrar, without registrar's help, I don't think we could have eaten such a good food. I mean, it's not a joke. That vendor was giving really very high charge. He was asking us, and we just could not afford it. And then registrar said, don't worry, you want to give this? We two were in meeting, he said, I will manage. And I don't know what he did, he reduced a lot, okay. So definitely thanks to Registrar for good food. And then actually, yes. After that, Jagdish Patil and Shiva Prakash and Akshata and all who manage all these bouquets and all other stuff. And then Somshekhar, who with help of volunteers, taxis and travel, and so complicated, you know. Every speaker comes, they tell they will go at 4, then they decide to go at 6. Somebody says, I will go in the night, then they say, I'm not well, I want to go at 2 o'clock. And it becomes pretty complicated. That Arjun Verma, I don't think he has slept for a few days. Yeah, so thanks to Somshekhar for taking care of all these things. And I just should not forget, special thanks to Swati and her team. We were very particular that we wanted you people to record lectures, okay? So I don't want to say it, but you people were busy in Yamini. I know how much pressure she has, but she agreed, and with smiling face, she has been recording for last 2 days. So Swati and her team, really thanks. Okay, and then I have just written, I don't want to forget anybody. So next is of course speakers. We got fantastic speakers. They took out time from their busy schedule, came here, and you know it's not easy to give lectures to mixed audience. I mean, I give lectures to mathematics people, I know exactly what type of lecture I have to prepare. But when IIM Tech first years are there, PhD students are there, industry guys are there, you just don't know what you can talk, what you can take granted. And just balancing that is extremely difficult, and all speakers did fabulous job. And I'm sure even first years could understand 15-20% of each talk. And that is great achievement, just believe me, okay? So thanks to all speakers for coming and giving talks here. In fact, coming to Bangalore from airport to here is also not easy. So I really appreciate all of you. Yeah, after that, of course, volunteers. I mean, you know, this show was run basically by volunteers. Myself and Srinivas Vivek, we were just giving them directions and nothing else. But from designing of notebook and posters and banners and bag, and finding vendor, calling them and following it, going and picking up bags, everything they did. And what we have to do? Nothing. Just one night we gave pizzas. That's all. I mean, and they have been working very hard and so enthusiastic, and I mean, hats off to you guys. I mean, all of you. I really, without you people, this would not have happened. Thanks a lot. And at the end, hardly any audience is there.
Actually, there were 38 in the room, like it's pretty.
Yeah, okay. So without them, what is conference, right? So this time we got really good response. So thanks to everybody who came.
Well attended RMIT edition.
Yeah, this is most well attended RMIT edition, and maybe Srinivas Vivek is lucky, lucky chap for this conference. I am attached to this for 9 years, and beginning there are hardly 5-6 people used to be there. In fact,
hard work is paying off now.
I used to write the speakers, you know, there may not be anybody except you people and myself. So do not mind, and you know, still they came and gave lectures. So it has been now growing and it's taking really good shape. So I really hope that even in future NBHM will keep funding us. I mean, you have seen now, sir, it is growing and we need more support, right? So we really request NBHM to take it seriously and increase our funds, and thanks a lot. So here officially I am closing this conference RMIT 2018. So, yeah.